Is all right. So yeah, welcome everyone to Iterable. So yeah, I've joined the company about 6 months ago, and in that time, really kind of fallen in love with the company culture, the people here, and also the product. I think it's really compelling product. So let me tell you a little bit about it. We're building a platform, a SaaS application for growth marketers. So these are marketers at companies like Spotify or Munchery, B2C companies. They're looking to retain their users, and get more users involved. Kind of keep engagement going. And so they need a lot of help with that. It's pretty involved. You got to send emails, you got to send text messages, push notifications, and we help them track and manage all that. So you can schedule email campaigns, you can set up user lists to send out campaigns at different times. You can put users through workflows, where like an onboarding workflow, for example, when you join the company for the first time, you get sent a series of emails to let you know about here's what's available in the product. And all this, as you might imagine, requires a lot on the back end, because not only are we having to support our direct customers who are the marketers at these various companies, but we need to support all of their customers. So all of their users who get these emails, who get these messages, they're going to be opening the messages, they're going to be reading them, clicking on them. All these events go into our system, and we track them and make them searchable, queryable by our customers, so they can get analytics on how their campaigns are going. So definitely a place where scale is very important. We use Elasticsearch, Postgres, Redis, and RabbitMQ in the back end. Those are our main data services, and are looking to scale up tremendously this year. So we're going to be scaling the product and scaling the engineering team to match. So we are definitely hiring. If any of this sounds interesting to you, please let me or Melanie, our recruiter, know. We're looking to have 2018 be like the most awesome year yet at Iterable. So thank you.
Oh, yeah, that's right. Yeah, we should just go.
Okay, this works. Okay. All right, I'm Tom Kim. I also work at Iterable. And today we're going to talk about type classes. So we gave a talk at Scala by the Bay around Shapeless. And here we're going to give a more extended sort of tutorial around just using, which is a more sort of basic level or more detailed level around using type classes in general. So how many of you are already using type classes in your code? And how many of you would like to learn more about them? Okay, perfect. Well, this is for you. So Shapeless. So type classes, I like to describe them as the most important thing in programming since object-oriented programming, which sounds hyperbolic maybe, but actually,
I don't think so.
No, not at all. So, and the reason that's so important is for two reasons. One is that type classes solve a large class of problems that are very common in programming. It overlaps quite a bit actually with the type of problems that are solved with object-oriented programming in terms of allowing you to program generically and with a level of abstraction over abstracting over structure. And the other reason is that type classes in Scala are a gateway to many of the more advanced Scala things that you've probably heard about, libraries like cats and Scala Z, and libraries like Shapeless. And so if you want to understand those libraries, you need to understand type classes first and sort of have used them in practice. And so in this tutorial, and there's very excellent resources online for this, including the Type Astronaut's Guide to Shapeless, put out by Underscore. In this tutorial, we'll give you an introduction to type classes and how to use them and how they work. All right, and I apologize in advance, I have a cough, so if you hear horrendous sounds coming from me, it's just that. Okay, so actually, do you want me to hold that? Yeah, you want to hold this?
Sure.
Charles and I are very affectionate of each other, and we work as a team. Not just because the mics have to work that way.
Yeah.
Okay, so we're going to do a live coding demonstration here.
That actually.
How about this instead?
I like the other way better, but. Okay, all right. So to demonstrate type classes, we're going to start with a very simple example. We'll start with a very simple thing that one might want to do, which is define an interface for printing things. And so that's commonly called the show type class. And if you were to do this in sort of an object-oriented way, you might define an interface show and define a method on that called show that returns a type string. And already when we do this, we run into a few problems with the traditional approach using interfaces. The immediate problem is that you cannot have show be implemented by your primitive types, Boolean, string, and so forth, because you don't have control over those types. Type classes allow you to do a lot of things that you can do with interfaces, but they solve three problems that you commonly face with interfaces. The one problem that you see here is about modularity. So because when you use interfaces or extension or inheritance, then you necessarily have to redefine your class hierarchy, and that won't work for primitive types. And there are a couple other advantages type classes have that we'll see later on. They work better with respect to modularity, they work for primitive types, and they compose in more powerful ways than traditional interfaces. So in a sense, type classes let you reuse the type system of the language that you're working in, which you can't do with traditional interfaces. So let's see how we solve this problem using type classes. So with a type class has three parts. The first part is the type class itself. And so to turn this interface into a type class, it's always going to be a generic type class over type T. And then there are the so-called instances of the type class. And so in this case, we'll define a few instances. Actually, I don't need to make it in this object in this case. So you define type class instances for each type for which you want that type class to type class support for that type. So in our case, let's say that we want type class support for some primitive types. So in that case, we define the instances for the primitive types that we want to support. So let's say we want to support integer and string and Boolean. Then we would define the instances by creating basically a global instance of value of the type show for T, or for that particular T that we care about, so in this case int. And we would just do that. And
yeah, and we make it implicit so that it can be found by the compiler with implicit search. And you'll see where that comes in a moment.
what happened here? Huh, okay.
Did show need to take a parameter?
Show just takes, so in this case, oh yeah, you're right. Yeah, so we want to make this like that, right? And so the second part is the instance, and the third part is the usage of the type class. And so in this case, we're going to define a method that uses the type class. So this is a method that makes use of the type class. So if you haven't seen this syntax before, this desugars to the following. So in Scala, type classes are all done by convention by way of implicits. And so let's call this tshow. And then we can call that with, for example, that, and this should return. Yeah, can make it even bigger.
Yeah, the other side too. Yes.
So again, there's three parts to the type class. The type class itself, the instances, which are defined as globally available implicits, and then the usage of the type class, which requires the implicit as a parameter. In particular, the implicits need to be available in the usual way according to implicit scope. And if you want to find further instances, then code here. Oops. Just copy this. Oh, I see. So we can also define instances for other cases. And then we can use those instances. Now we can say that true. Note, importantly, that if you pass in a value of a type that's not supported by the type class, meaning no implicit instance exists for that type class, then your code will not compile. So in this case, if we pass in, so let's remove the instance for a string, for example. We pass in and this code should fail to compile. I'm not sure how that'll look in the worksheet. Because the worksheet just doesn't do anything. But suffice to say that code doesn't compile. It'd be good to see the error message. See what happens if I do this button here. Okay. Refresh. Try this mode.
It looks like it's showing an error in the upper right corner.
Oh, right here.
Yeah,
Oh, yeah.
but no information.
Well, just so you know, this doesn't compile. So far what I've shown you seems like kind of interesting, but maybe not that powerful. So we'll start seeing some more advanced uses of it. So one thing that type classes can do that's really powerful is that they compose. And so a really common thing that you want to do is you want to define an instance of show for option. What's interesting about option is that option is parametric, so it takes a type parameter. So how do we do that? So to define an instance for option, you need to do the following. So basically you want an instance of show of that type, but it needs to be generic. So what you can do is instead of using an implicit val, you can use an implicit def. And your implicit def can take a type parameter t. And then we can provide implementation of that type parameter. But in order to provide an implementation of that type of show for option of t, we need an instance of show for t itself. And so you can express that requirement by adding an implicit argument to the implicit def called tshow. And now this implicit def will be available whenever tshow is available. In particular, whenever show is available for one of the primitive types, or it can also work recursively. So in that case, since we have a helper method here, we just do this show, and we'll just delegate it to string. And so now we can do show of sum of 5, and if this doesn't screw it up,
I think you need to comment out. Yeah.
then it'll compile. There's something else wrong with the worksheet here.
Anyone know how to show errors in a worksheet in IntelliJ?
Looks like show, it doesn't show off.
Right. Scroll to the
Green arrow top left.
green arrow, top left. Top left.
This one? The top left.
Yeah, the green
Oh,
arrow.
yeah.
So there must be a failure after that.
Oh, yeah.
Maybe it's the private.
Probably a syntax. Yeah.
Private, yeah. That's probably what it is.
Show int.
Try that.
paste that whole block into the REPL?
Yeah, I'm gonna fill, yeah, we could try that.
And
Apple?
that was like nothing.
Huh? Yeah, we could try a new worksheet. How about that?
What if you click use REPL?
Yeah, okay, let's try that.
Yeah, try hitting refreshing it again.
Aha.
There we go. Nice. Okay, I think we're back in business.
So this worked up to here.
So it didn't like the option.
Yeah. Oh, it doesn't like that, you think? Let's see if it likes this. True. So it doesn't like the option. So what's missing in the option here? Show option of T. T show T. Helper. Let's try.
Yeah, you gotta do some, right?
Let's
Yeah.
see if show.
Try that now. Right. Yeah, hit the play button again. I think that did it. This is the wrong. Oh, the T show. Look, it's like.
So T show, T string.
It's not a.
Did you do in the type 2 in this one? Try. Maybe that didn't work in there.
All right. Well, should we come back to that?
Yeah, we'll come back to that. That should work. Okay, so if that example worked, then you'd see that type classes compose. And so the way that the implicit search works, in case it's not clear, when you write code that uses the type class, it looks at the required type of implicit that you need. So in this case, we'll require, when we call this show function, that there be a show instance for that T. So it's going to search for an implicit of type show of T. And so we have instances for show of char and show of boolean. We have instances for a show of option of T, where this implicit is required. And so to satisfy that implicit requirement, it not only searches for the implicit instances defined as vals, but it can also search for implicit instances that are defined as defs, and recursively search for the implicit instances that are required to satisfy that def. That'll be an important piece of functionality that we'll see later. So now we're going to take an aside and talk about something that seems somewhat unrelated, which is type level functions. And so type level functions are pretty commonly used. You've probably all used a type level function. And so an example of a type level function would be any type constructor. So if you've ever used list, you've used a type level function. List is a type level function that takes the type T to the type list of T. And so it's sort of self-named. There's a couple other sort of trivial encodings of type level functions within Scala. One is type aliases. And so you can have a type alias called, say, foo of T. And that will give you a new type, which is the pair of T with T, for example. And this is another somewhat trivial example of a type level function. You've defined a type level function called foo, which takes as a parameter T and gives you a result type, which is the tuple T of T. Now, there's a more sophisticated encoding of type level functions in Scala, and we call these dependent types. And they're used throughout libraries like Shapeless, and they fit pretty closely with type classes, and so we'll show how that's encoded. So an example of a type level function is a type constructor that takes a type as a parameter and then yields a new type. So there's another way that you can code type-level functions in Scala, and that's using path-dependent types. So you can have a trait, and for example, we are going to define, we're going to call this make option for reasons that we'll see. And it's going to take as an argument a type parameter called t, and it's going to yield an output type that depends on t. And that output type will be contained in a type member called out. So what's going to happen is that we'll have instances of make option, which declare for particular values of t, or for particular types t, a particular output type out. And this output type is defined as a member, as a type member of this trait. Now, pretty commonly when you have, or almost always when you have a type level function, you have a value level function that goes along with that type level function. And so in this case, we'll have, we'll call the method apply. It's going to take a value of type t and then return a value of type out. And so as an exercise, as an example, the type level function that we're going to define is going to be a function that says, for all types t, give me option of t, unless it's already an option. So you may never have done that before, and we're going to show you how to do it. And so you can do this.
So the output will always be an option. It's just that if it's already wrapped in an option, it won't do any more wrapping. That's basically the idea.
So this is, again, is done by way of declaring make option as a type class. And so in our type class, we start by defining an instance for things that are already options. So if it's already an option, then your output type is simply going to be the same as the input type. So since it's for option, option is parameterized, we need to make that an implicit def. So we'll just call this option as option. So basically, when you're searching for an implicit instance of make option for something that's already an option, then use this instance of make option, whose output type is going to be just that same option again. And the value level, just make it the identity. So now we have a type class, which the implicit instance, or the instance of that type class, for types that are options, is simply to return that option type. Next, for all other types, we want to return that type wrapped in an option. So we use one trick here, which you'll see in a lot of libraries. We'll move the implicit instance for the fallback case into a super trait. By moving into a super trait, we basically tell the compiler to use this in the fallback case, meaning use this instance with higher priority than the instance that's in the super trait. And so in the super trait, we can say non-option type should be wrapped.
Yeah, this is necessary because this case is just going to apply for all types T, and so you don't want it to conflict with the definition that's specific to option T.
So now, if we do, for example, so now we have this type class, we have instances, so if we try to use it, so let's actually have a function called make option, which takes a type T, and then is going to give us a value that's always wrapped in an option if it's not already wrapped, or if it's already wrapped as an option, then just simply yields T. So to use this, we require that a type class instance exist for T, and the permission is always going to exist. And importantly, this function it requires make option as an implicit parameter, and then it's going to return, again, this is a dependent function. So the type that it returns depends on the input type. So to express that, you can say that the return type is the type member out off of this implicit parameter. So clearly this function is dependent. So if this works,
on line 41, should that be a sum to the right?
yeah, we can make a sum or option either way. So if we call this, so the claim is that if we call this function with a simple type, it'll return that type wrapped, or that value wrapped in an option.
We have to reload it again or change the mode that you're in.
Change the mode.
Yeah, because it hasn't been going line by line.
At this point, yeah, I wonder if there's something wrong up here.
Just try reloading it.
Maybe just try commenting these out or something. Looks like there's something wrong here.
Did you uncheck a box?
Is that?
Oh. It's right there.
Oh, okay.
Yeah.
Could not find implicit for make option at end. This extends.
There we go.
Okay.
There we go.
This is real code. And sometimes it doesn't compile. Let's see. Let's try it again here.
Try reloading.
Okay. Make option of end. So we did this. This. Oh, we know what it is. I think this is conflicting with the other worksheet, maybe. Is that the problem?
Maybe close the worksheet and reopen it.
Maybe, is that what the issue is?
Yeah,
I think that could be the
it's
issue.
got some cached state in there.
I think so? Oh, I see. Okay. So let's try, I wonder if this worksheet is better, actually.
Oh, actually, no, here's the problem. Because it's a worksheet, you can't define a trait and a companion object together. See, it's giving you a warning.
Yeah.
Mm-hmm.
So change the name of the object.
Yeah, change it. Yeah.
Change the name of the object and then import it. Yeah, it's not gonna work. Let's
Yeah.
try this. No.
Oh, turn it off in REPL mode. Try it again.
Oh, yeah, okay.
Yeah. Just turn off REPL mode. That'll probably do it.
Oh, I see.
Yeah. Reload. Yeah, here we go. Thomas Warriors. Comment that out.
Ah, there we go. All right, so you can see it wrapped it in an option. And if we did this properly, then if it's already wrapped in an option, then it'll actually just return the value. Oh, I wrapped it twice? Oh. So this is not option wrapped.
Oh, it's because it's sum. You change it back to option.
That has to be option,
Yeah.
actually.
Because
think that's
otherwise
right.
it infers the wrong type.
I don't know about that. This.
Reload.
I think you might want to change that muck option to muck option 2.
Yeah.
Yeah.
So change this back?
Yeah. Because now we're not in REPL mode anymore.
Okay, let's try that. Oh, because only the low priority is coming.
Right. Did that actually reload it?
Doubt it. Huh.
It's getting inferred as sum instead of option.
So what was came
Oh,
as,
yes, good call. Yeah, down at the bottom, TK. Change that to option.
could be it. Yeah, that could be it.
Yeah.
Pretty sure this worked when we tried it locally, but.
That is a temporary variable, so you don't get
Right.
directly.
Ah,
Yeah. Good call.
good catch. Okay. So, some gotchas, but you can see the overall goal is, so we have this type-dependent function given by a type class, which varies as a result type depending on the input type. And so if things are already an option, then it doesn't wrap it again.
Hey, Tom,
Yep.
but you plan for this to work with some, right? And is there something
Yes.
wrong with it? I mean,
There are definitely ways to make it work with some. Offhand, I don't think I can fix it live here.
no, I just want to know that if somebody wanted to use that with some, that it would in fact work.
Yeah, there's a couple different ways to do it. I'm pretty sure the direct way to do it would be with variance. So I'm not going to experiment with it here, but it can be as simple as just adding a plus here. But I'm not going to, well, okay, I'll just try it, but I don't think that'll work exactly. Oh, maybe it did. Okay.
Oh, cool.
All right. Did you reload?
But with variance, things do start to get hairy with using type classes. Yeah, I'm pretty sure it reloaded. So that seems like one small step, but combining these techniques, we're gonna work ourselves up to doing all the powerful things that you can do with Shapeless and other type class libraries. And so to get into Shapeless, and you'll see why these approaches are so important for a library like Shapeless. We're going to take a small interlude to talk about HLists, which are really important in Shapeless. And so,
So yeah, the idea behind HLists, they're kind of like tuples, right? Where every element in a tuple can be a different type. Why Shapeless has HLists, though, is so that there's a sort of a base class or a common way to refer to all of the values. It's as if all tuples had a common base type, and that will come in handy, as we'll see with some of these implicit type class definitions.
So we'll actually just take a quick peek at the Shapeless source and just a quick peek at the definition of HList. And so HList is it's defined almost very similarly to the way list is defined in Scala as a linked list. But it varies in one important detail, which is in the cons case, you have a head and a tail. So actually, if you look at list in Scala, it's an abstract class, and it's got two cases. It's got nil and cons. And so in the cons case, there's one type parameter, and you have the head is of that type, and the tail is a list of that type. In the HList case, you have two type parameters. You have a type for the head, and you have a type for the tail. And the head is its own type, and the tail is recursively defined as another HList type. And so in that way, HList is similar to linked list, except it preserves the type of all of its elements. And so when we use an HList, so like this HList here, it'll have the type. I should just switch to REPL probably.
Yeah.
It'll have the type of string, Boolean, and HNIL cons together. So
I got another error.
so that never actually worked actually, because that doesn't. Yeah. Okay.
Yeah.
That's interesting. Okay. So anyway, with this HList, you'll see it preserves the type, so it's type string, Boolean, and then HNIL. And so if we look at Shapeless, Shapeless provides an important piece of machinery called generic. And generic by way of a macro, provides a transformation from any case class into an HList representation of that case class. And so for example, if we have case class account, which has 2 fields, apologize, this keeps clearing the screen each time. And there's, you can actually invoke generic as an apply method on it, which returns the application of the generic type class to account. And you can see it has, so if we look at the definition of generic, you'll see it's
Zoom in a bit more.
it's a type class, and so it takes a type parameter, which we've all seen before now with type classes, and like other type class or like other dependent type classes, it has an output type that's called repr. So this is another example of a dependently typed type class. And at value level, it provides functions which transform instances values of type T to repr, and from repr back to T.
So repr is the HLists representation of the type T. It's the generic format of it.
So if we go back to our generic account, it's going to produce a type of generic where the type member repr has the desired HList type. So in this case, string, cons boolean, cons nil. And does that by way of macros. So now, one thing that we want to do with the show type class that we weren't able to do before is create an instance of that type class for all type classes.
All case classes.
Sorry, for all case classes. And so you can see why that would be useful. We created instances for int and string and boolean. We created instances for option. But what we really want at the end of the day is an instance of show for all case classes. And Shapeless lets you do this. And so to do this, I'm actually going to just copy these in. We've already implemented. There's a certain pattern for how this is done. And what we do is we create implicit instances for 2 cases, hcons and hnil. So the implicit instance of show for hnil is trivial, it returns empty string. The implicit instance of hcons, of show for hcons, requires implicit instances of show for the head and tail, and then provides an implicit instance of show for hcons t, which implements show, delegating to those other show instances for the head and tail. So this is exactly what we did before when we had when we were composing show instances for option. It's just like somewhat more sophisticated. So again, it's also recursive, and these are called inductive implicits. And
Yeah, like one way you can think about this, like with sort of ordinary Scala programming where you might do a pattern match on a list and have 2 cases for the cons and the nil cases in the pattern match. This pattern here is the same thing. It's a pattern match, but because we don't have in a normal pattern match, you can't have different types on the different cases. In order to support the different types in the HList, the different cases have to be different definitions with different parameters, generic parameters. So we've taken the ordinary pattern match construct and sort of lifted it to this implicit search level, where the Scala compiler will actually end up sort of traversing over the structure of the HList as it does an implicit search.
yeah, and so the reason it's called inductive implicits are because we're building up the implicit instances one by one, starting from hnil, then going from a single element HList to a 2-element HList and so forth. And the 2-element HList instance, the case for the 2-element HList delegates to the case for the 1-element HList and so forth.
Should we try it out?
Yes, I'm sure it'll work perfectly. So actually, there's one more step that we need to do, which is we need to convert an arbitrary case class to generic representation, and then apply the show for the HList representation of the case class. And so we just define a helper method. Actually, I'll just copy this in.
So it's somewhat
for case classes, we can implement a show method. That show method requires that there be a generic representation of that case class, and then a show instance for the generic representation. We haven't talked about this aux thing, but as we mentioned, these type classes, which are dependent function types, they have an input type and an output type. And this aux thing basically lets us extract the output type, which we're calling R in this case, from the case class. So basically, the thing that's buried as a type member, repr, we can extract it as R. And then we use, conveniently, the value level functions that are provided by the type classes are always exactly what you need to implement the instance. And so in this case, we need to convert. So given an instance of the case class T, we convert it to its generic representation R, and then we take the generic representation and invoke show for that generic representation. And so if the worksheet cooperates with us, then we should be able to do
reload again, probably.
account. I define account.
Yeah, try reloading again.
Well, we're going to invoke it. So you can. This could be either
There's
implicit
another error.
or explicit. Yeah. Okay. So we can.
That's strange.
Please show instead of case class show. Just show.
It's saying not enough arguments.
That doesn't
Case
matter.
class show.
I think what we need are.
Try checking it out. Is it in REPL mode? Try taking that out and reloading it.
No. I think this works better when we put these inside the. I think it's having problems finding these implicit instances out of the worksheet. I think it works better if I put these in the like this. I don't think that'll work in this worksheet either.
No.
I'd be surprised if that worked. So unfortunately, we'll have to test this better next time. But
Could you just manually pass the implicit parameters? That's what it's complaining about right now.
what's that?
Are you missing a closing brace? Is
Maybe.
this all in an object?
Yeah.
I don't think so. The error would be different.
Is this ready?
It would have a different error, I think.
Oh, the hcons case and the hnull case, right?
Try reloading again.
Shouldn't this be show instead of case class show? If you wanted to
Well,
case
we-
class, right?
It needs to be case class show because we have to pass a case class into it. So that's the, we're missing the parameter list for the case class. You have to have a parameter of type T. Up.
for where?
Oh, it's case class show dot show. That's what it is. Case class show dot show. Right? No.
Oh,
Right.
yeah.
You have to do a bracket account for,
Yeah.
right? Yeah.
We wanted to define a show instance for
That's right.
So we had this function show, which is like generic function to show something. Shouldn't we use the same? Don't we
Oh,
want to
I
use
see.
the same
Yes, that's right. That's
Actually, I
right.
can
It's just
just do
show.
this.
It's just show. Yeah.
Well, if I made it
yeah,
like that, I wanted to make it explicit, so I
No,
can
so
do this.
we have to just use we already have a method called show that gets the type class.
Yeah, if I made this implicit, I could do that.
Uh,
For this, I didn't want to. I could try that though.
no, take the parameter out of there. Use the show method directly. Instead of case class show, this is defining. Do an implicit def actually.
Make this implicit, right?
Implicit def. Yeah.
Yeah. I'm not sure that'll work.
And
right here, but we can
then
try
just
that.
use show. Yeah. As long as it's in scope. Did we? I think we commented that out further up though, didn't we?
Let's try this.
Yeah, we got rid of it. We got to get it back.
Okay. See if that works.
Yeah, we commented it out from before. Of course, now it might not have.
The main thing is don't use worksheets for a live coding
Now it can't
demonstration.
find implicit values for the parameters, probably because we commented some of them out. Right.
Yeah. Okay. Well, we can move on too, because there's more to talk about.
Sometimes it gets started, you cannot get back.
Yeah.
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 This is a bit of an experiment today.
Yeah.
Play button every time you're done.
Okay. Well, suffice to say that this will give you a show instance for show, and it'll print out the case class using those instances. So now to talk a little bit more about Shapeless.
40 minutes.
Okay. So the last thing we want to show you are that, so HLists have many of the usual methods defined on them that you would expect for, say, a seek or a list. You can do head and last. A cool thing that you can do is you can do drop one, but things like drop, it knows statically the length of this HList, and so drop 1 and 2 will compile, but drop 3 won't. And what we want to show you was how these things are actually implemented by Shapeless. There's also a cool function on HList called select, which will select out of an HList the field of the type of a specific type. So if you call select bracket string, then it'll select for you the field of type string, which in this case is name. And so all of those operations on HLists are defined as type classes, interestingly. And so if we look, for example, at the function select, oh, okay. Yeah.
Could probably just get the definition in there.
Let me do it over here. Let's see, let's do that. So if you look at def select, you'll see, just like the code we've been writing so far, it delegates to a type class and then simply invokes the apply method on that type class. And if you look at the definition of this type class, you'll see it's implemented just like the code that we've been talking about. It has cases for the hcons case and for the, well, I guess it has a case for hnil because that'll never work. And this particular type class has 2 type parameters, a type for the HList and a type called u for the type that you want to search for in that HList. And it provides an instance for when, and then it has a hcons case for head and tail for where the head and u are equal. That's defined right here. And in that case, it simply returns you the head. And it also has cases for, this is essentially defined as a fallback, where head and u are not equal. And in those cases, it recurses over the tail. And just as before, these instances are only available if the HList contains some case where u is a member of the HList. and otherwise it'll fail to find this implicit, and it'll fail to compile. And so much of the code of Shapeless is simply implementations of these type class instances. So one of our main goals in this tutorial is to give you enough knowledge about how type classes work, to understand how to read the code behind Shapeless. And there's many, many more operations that provides. Things like align, so that you can take two case classes with the same names in different orders, or fields with the same name but in different order, and map them to each other. Ways of lifting case classes into other type constructors or type classes. And more broadly, you can use these approaches to implement all kinds of generic programming solutions for all kinds of generic programming problems. So these occur commonly with things like configuration, when you deal with ASTs.
Database schemas.
Exactly. And yeah. So that concludes our tutorial.
Any questions about Shapeless, type classes?
Great. Aside from the worksheet problems, I hope you're excited about using type classes in the future.